Hey guys, Professor Calculus is here, and today I'm here with this integral for you to solve x to the power of x squared. So, unlike other integrals, this integral cannot be used using power rule, and you have to use other techniques to solve this integral. Before, make sure to like and subscribe, and as it is free, and you can always change your mind later. So, first of all, if I have any number or variable, for example x, I can raise it to the power of e to the ln x and still get x. So I can use this trick to change the form of this integral here. So I'm going to use this trick and I'm going to say I is equal to the integral from 0 to 1 e to the ln of x squared dx, and thus I is going to become, according to the property of the logarithms, it's going to move here. It's going to be e to the x squared ln x dx. Now, what I'm going to use here, I'm going to use the series for e to the x, which is the infinite sum from 0 to infinity of x to the n over n factorial. And if I plug in x squared ln x, I'm going to be getting the infinite sum from 0 to infinity of x to the x squared ln x to the n over n factorial, which is going to give me the infinite sum x to the 2n ln to the n x over n factorial. So what I'm going to do, I'm going to replace it in my integral here, and my integral is going to become the integral from 0 to 1 of the infinite sum from 0 to infinity of x to the 2n ln to the power of n x over n factorial dx. And I can move this n factorial because it is constant with respect to this integration. It's 1 over n factorial, the integral from 0 to 1 of x to the 2n ln to the power of n x dx. Now, here I can use a variable substitution. I can use a substitution variable. I'm going to let t be equal to negative ln x. Therefore, ln x is going to be negative t, and x is going to be e to the negative t. And if I differentiate both sides, I'm going to get dx equals negative e to the negative t dt. Now, I got to change my bounds, obviously, and if I change my bounds, I'm going to be getting, when x equals 0, t equals infinity, and x equals 1, t equals 0, because ln of 0 approaches negative infinity, and negative of negative infinity is infinity. So I'm going to write this integral again. N equals 0 to infinity of 1 over n factorial from infinity to 0 of e to the negative t to n negative t to the n negative e to the negative t dt. And according to the properties of integral, this negative can be absorbed here. I can pull it out, and I'm gonna let this negative to be here, from infinity to 0 of e to the negative 2nt negative t to the n e to the negative t dt. And this negative sign flips the sign of the integrals. If I have, for example, negative a to b f of x dx, it is the same as b to a of f of x dx. Now I can use this property to say the integral is from 0 to infinity of e to the negative 2nt, negative t to the n, e to the negative t dt. Now, I'm going to expand this integral a little bit more. 1 over n factorial e to the negative 2nt minus t, negative t to the n dt. And I'm going to just sort it a little bit more. E to the negative t times 2n plus 1, negative t to the n dt. So this integral is getting really interesting right now. So the infinite sum from 0 to infinity. Now what I can do here, I can expand this negative t. I can say it is negative 1 to the n times t to the n dt. And I can move this negative 1 out. I can say from 0 to infinity of negative 1 to the n over n factorial, the integral from 0 to infinity e to the negative t times 2n plus 1 t to the n dt. Here I can use another variable substitution. I can say that u equals to t times 2n plus 1, thus t equals u over 2n plus 1, and dt equals du over 2n plus 1. And the bounds are going to be staying the same, so I'm not going to write it here. And if I substitute it again, the infinite sum from 0 to infinity of negative 1 to the n over n factorial, the integral from 0 to infinity of e to the negative u over 2n plus 1 to the n du over 2n plus 1. And my I is going to be the infinite sum from 0 to infinity of negative 1 to the n over n factorial, the integral from 0 to infinity of e to the negative u to the n over 2n plus 1 to the n times du over 2n plus 1 to the 1. Now, according to the power rules, the laws of exponents, e to the negative u to the n du over 2n plus 1 n plus 1. I can write this, can sum up the powers. And you're almost there, hold on. I can move this out here, and I can say negative 1 to the n over n factorial 2n plus 1 n plus 1 e to the negative u to the n du. Now what do we do with this integral? This integral is a little bit long to solve, but actually this is equal to n factorial, and it is pi function, and perhaps I'll do it in another video and prove that this is indeed equal to n factorial. Thus I can suppress this one and this one, and I'm going to get n equals 0 to infinity negative 1 to the n over 2n plus 1 over n plus to the power of n plus 1. And finally I'll get the answer of my integral from 0 to 1 of x to the x squared dx to be equal to the infinite sum from 0 to infinity of negative 1 to the n over 2n plus 1 n plus 1. And that is the full answer of my integral. And you can go ahead and see the approximation. I don't have the numerical approximation here, but the series does indeed convert. Thank you for watching this video. Please make sure to like and subscribe, and I will see you next video.